Okay, so we have uh, looked at the concept of a basis, and we are also aware that basis is not unique. You have typically infinitely many different kinds of bases that you can construct for a given vector space. Uh, Although the number of elements in every basis has to be the same, that's the dimension of the space, and we have been concentrating on finite dimensional vector spaces. Right, so in this lecture we look at what happens when you go from one basis to another. Right, within the basis we have seen that all operators have representations, matrix representations inside every basis, and so when you transform, when you change basis, the representation is also going to undergo a change. So vectors would change from one basis to another, how they look, and likewise the representation for operators also will change. Right, that's what we're going to look at in this lecture. Okay, so suppose you have a basis BE, I'm calling it BE, and you have another basis BF. Right, so the first basis has the elements E1, E2 all the way up to En, and the second basis has the elements F1, F2 all the way up to Fn. Right, so necessarily both of them have exactly the same number of elements, that's n, right, because the dimension of the basis of the vector space is n. Right, so each of these bases will have n elements. Now at this point I am not demanding that either of these bases must be orthonormal. Right, that's a special kind of basis. We will come to that a little bit later. So let's start very general. We have two generic bases. So since BF is a basis, every element of BE, right, I mean every element of BE is a vector which belongs to that space, and so it can be expanded as a linear combination of the vectors of BF. So if we do this, you have EJ can be written as summation over Tij Fi, summation over I. Right, you can find some coefficients Tij. Right, for the jth vector in this basis, you can find the coefficients Tij, and I goes all the way from 1 to n. Now, so where we have defined a matrix of coefficients Tij. On the other hand, BE is also a basis, and every element of BF can also be expanded as a linear combination of the vectors of BE. Right, so Fj itself can be written in terms of some other set of matrix coefficients, some other set of coefficients Sij. Right, you sum over Ei, sum over I, Sij, Ei. Right, so you will always be able to find these coefficients such that every vector in one basis can be represented in terms of the basis vectors of the other basis. Now if I start from equation 2, Fj is this, but then in place of Ei I will plug back in the expression from equation 1. Right, so then this will give us a constraint for these two matrices. So I have introduced this matrix of coefficients Tij and another matrix of coefficients Sij, but they are intimately related. That's what we're going to extract from doing this exercise. So Fj is summation over I Sij, but in place of Ei I will put in summation over k. Right, it's a dummy index, I can choose k because I have to work with I here. So Tki Fk, and then I combine, I exchange these summations. So instead of summing I first, I'll put k first, and then I will club these two, summation over I Sij Tki is and then there's an Fk as well. Right, so this is possible only if so it's more convenient to actually rearrange this and write this as summation over I Tki Sij. Right, so then you see that this is in the form of the product of two matrices. If I think of T and S as two matrices, then their product, right, must satisfy this condition. It's going to be a diagonal matrix, and in fact all the elements in the diagonal must be 1. Only then will you get back Fj. Right, you have a sum over k, but all these coefficients except when k is equal to j must be 0, and when k equal to j it must be 1. So the compact way to represent this is to say that this summation is this Kronecker delta kj. Right, another way of saying this is that T times S, the matrix T times the matrix S is equal to the identity matrix, or equivalently S and T are inverses of each other, right? So that's what is the connection between these two transformation matrices, right? You go from one basis to the other, and there is a this basis transformation necessarily must be invertible, right? You cannot have any non-invertible transformation. If you go from one basis to another, then there is a way to get back to the original. So there is no loss of information in going from one basis to the other, right? That's what is meant by it being a change of basis. Okay, so necessarily both these transformation matrices are non-singular, right? If it is a singular matrix is not invertible, as we know. Okay, so what happens to matrix representations? How do they transform, right? So we have looked at the basis vectors. So in general, vectors also undergo transformations, but so do operators, the representations of operators, right? Operator is an abstract quantity. Nothing happens to an operator if you change basis, but the representation of the operator is different in different bases, right? So let's say you start with BE. So you have E1 all the way up to En, and then to find out what this operator looks like in this basis, you must find out what it does to each of the elements of this basis, right? So like we discussed in a few lectures ago, right? So we saw that A acting on Ej is summation over Aij Ei. So you explicitly work out what the operator A does to each of the vectors in this basis, and then so basically you need to find out all these coefficients Aij, right? So this is the representation for this operator in this basis, and likewise there is a representation for the same operator in a different basis, right? That's the other basis which I have called BF. Now to work this out, let us see how we can work out what this operator does to the elements of the second basis in terms of this transformation matrix and the matrix elements in the first basis of the linear operator. The representation of the operator in the first basis, we want to connect it to the representation of the same operator in the second basis. Okay, so in other words, what we are interested in is finding out what A does to Fj. So what A does to Fj is the same as what A does to summation over K Skj Ek, because we have written Fj as summation over this I Sij Ei. In place of I am putting K, it's a dummy index, it gets summed over. So I have in place of Fj, I put this summation, and then it's a linear operator, so it goes right through. So I have summation over K Skj, the operator A acting on Ek. Now, but I know what happens to this vector Ek when A acts on it, because I have written this out in terms of the representation in the first basis. So let me go and fill that information in. So I have summation over K Skj, summation over L, right? Again, it's convenient to use another index other than I here. So summation over L Alk El, right? So I'm looking at what happens to Ek when A acts on Ek, and so I can plug this in here. Now you expand El in terms of the second basis using equation 1, right? El itself can be written in terms of, with the help of Tij's, you can write it in terms of the basis Fi, Bf, right? So then you have one more summation comes in. So A acting on Fj is actually summation over K, Skj summation over L, Alk summation over I, Til, Fi, right? So you should cross check and convince yourself that this is indeed, I have used the right symbols everywhere. So now I can regroup these summations in this way. I'll bring the summation over I right at the beginning, then I have a summation over K, summation over L, and then it's convenient to rearrange these coefficients in this way, Til, Alk, Skj, which gives it a very suggestive form, right? And then finally you have a summation over Fi. Okay, so you see that this stuff inside the brackets is really the product of three matrices, right? So what is happening is, so we started with the representation Aij, but now you can see that this is the new representation for the same operator A, right? This is what we're interested in. What A does to Fj, right, must be written in terms of the same basis. That will give you a set of coefficients which will give you another matrix, right? We can call it Aij tilde if you want, right? So, but to avoid clutter, I'm going to just go to matrix notation. So you notice that I have TIL ALK. If you want, you can start with just these two and multiply these two matrices, and then you go ahead and multiply these two matrices, right? You should convince yourself that really what is going on here is nothing but the multiplication of the matrices T, A and S. But S is the same as T inverse, as we have seen. It has to be, right? Because these two are transformations from one basis to another and back. So therefore it has to be T inverse. So all that is happening is your matrix representation is getting sandwiched between these two matrices, one in the forward direction and the other in the backward direction. So you get T, A, T inverse. So which is a similarity transformation, as we have seen, right? Whenever you sandwich a matrix between some other matrix and its inverse, like here, then it's a similarity transformation, right? So thus the matrix representation of an operator undergoes a similarity transformation, right? So likewise, we could have also worked out what happens to any vector x, right? So if you started with some vector x, so you can expand in this basis, you get a bunch of coefficients xi, which we have seen can be thought of as a column vector, right? So under the change of basis, we have to just replace ei with summation over tki fk, right? We are interested in what it looks like in this basis. So, and then we have to regroup these terms, and I have a summation over k, this stuff acting on fk. So this stuff is the representation of this vector. So the vector is the same, right? It's an abstract quantity, right? If you wish, this can be, as different as you please, as long as, it satisfies the basic properties of vectors. But the representation is a bunch of numbers, right? These xi's. Now those xi's will have a transformation. If you go to a different basis, it will look different. Thus we see that under a change of basis, a vector is transformed to t times x, right? So you should, look at this and convince yourself that indeed all that is happening is, this vector going from x to tx. So the representation for an operator, has this change, and the representation for a vector undergoes this change when you do a change of basis, right? So now we look at what happens under a special kind of a basis change, or rather when you have two special kinds of bases involved, right? We have seen that it's convenient to work with orthonormal bases, right? So when you have orthonormal bases, you get some extra constraints inbuilt, right? Which makes also the transformation between these two such orthonormal bases also come with some special extra properties. That's what we will look at, right? So first of all, you have this completeness expansion, completeness relation, right, in each of the orthonormal bases. So identity can be written as summation over I, ei, but identity can also be written as summation over j, fj, fj. If you wish, this is a representation of your identity operator, right? And it looks basically the same in any orthonormal basis, right? That's what this result means. And we'll exploit this to get some more constraints here for when you make a transformation between orthonormal bases. So see, I is summation over I, ei. But ei, in place of ei, I will put in this, there is this way to go from, write ei in terms of fk. So I plug in this here, and then I use a different dummy index L here, I have a k here. So the bra vectors, instead of you get TLI, you get TLI star, right? The conjugate has to be taken. These are coefficients, and then if I group them all together in a nice way, then I have summation over k, summation over L, summation over I bring in right into the center. Then I have summation over I, TLI star, TKI, FK, FL. But this must finally equal Fj and Fj. This matrix representation for the identity operator has got to be diagonal no matter which orthonormal basis you're in, right? So that means this has got to be Fj, and that the only way that can happen is if you get a delta function here, right? So this quantity must go to delta KL, and then so all the double sum will become a single sum, and then you get only diagonal terms, right? So that's what that's the condition that is imposed upon these transformation matrices. But if you look at this carefully, this is the same thing as saying that T times T dagger is equal to T dagger times T is equal to I, right? This is just the same as a condition for this T to be a unitary matrix, right? So a transformation that takes you from one orthonormal basis to another orthonormal basis is unitary, right? So that's our result. So for a unitary operator or a unitary matrix, so we know that the inverse is the same as the dagger itself. So T inverse is equal to T dagger. So the similarity transformation, right, which operators undergo when you change basis. So instead of it being just TA T inverse is the same as saying it is TA T dagger for a unitary transformation. Okay, so that's all for this lecture. Thank you.